Bismillah ar-Rahman ar-Rahim. Welcome to EEE 223 Industrial Control class. We'll continue discussing the topics in Chapter 3. The fourth controller is the derivative controller. Before we are going to the derivative controller, we'll do a quick review. And we can see here, this is the feedback loop system, and we are focusing on this part, which is the controller part. Actually, one of the main functions of the controller is to compare between the set point and the process variable. The set point here is set by the operator, by you, while the process variable is coming from the real process by the sensors or from the sensor. And then we will have the E, which is the difference between the set point and process variable. And here we go, that's the controller will deal with this E or with this signal. After that we will get the M, which is the controller output. The first controller that we have discussed is the on-off controller, which is the simplest and the easiest and the inexpensive controller, which is commonly used in heating and refrigerating system. However, this control it's from its name, is on or off. That means the output of the controller will be either maximum or the minimum. The second controller is the proportional controller, which is the controller in this case, the controller output is proportional to the error signal. That means it will cause an immediate response of the controller output with respect to the change in the error. However, this one or this controller has disadvantage of inability to eliminate the steady state error, or what we call it offset. The third controller is the integral control mode, which has a function of elimination of the error, or it will eliminate the offset, which can be caused by the proportional controller. So here in integral part, it's the controller output is proportional to the integral of the error, and already we have discussed this one in the class. However, this integral control mode has disadvantage that it can cause oscillatory response or fluctuation in the output, or it can make the process very, very slow. So that's why we are having the derivative control or derivative controller mode. Is one of its function is to speed up the process variable or the process dynamic in order to have the process variable reaching the set point in very reasonable time. So here we can see the variation of the temperature or the process variable here. See, this is the process variable, and here we have the set point. So the process variable is changing and varying across the set point. Here is the controller output. You see it's off, on, off, on, off, on. So this is the case of we have on-off controller. For the proportional controller mode, we can see that the process variable, after some times, we will have, what we call it the offset, which is the difference here in between the set point and the process variable after, getting the steady state. In this case, we have the controller output M equals to Kc, which is the gain multiplied by the error. So we can notice that the proportional will cause immediate response, of the controller output to the change in the error. In this figure, we can notice the integral action due to the variation in the error. The process variable will take so long in order to reach the set point. However, we don't have offset here. There is no offset, in this case. So this is one of the advantages of the integral mode. On the other side, the response of the controller will be slower in order to deal with the integration of the error. As long as process variable is away from the set point, then the integral will keep adjusting m. So in case we have the set point equals to the process variable, that means the error here equals to 0, so the integration will be or the controller output of the integral part will be equals to the 0. For the derivative controller mode, first of all, this derivative cannot be used alone. It should be used with the proportional integral part or mode, or with the proportional and derivative. The controller output of the derivative is proportional with the derivative of the error with respect to the time. However, here we can say that MD equals to Kc, which is the control gain, multiplied by the TD, which is the derivative time, multiplied by the delta or dE over dt. So the TD is the derivative time, normally in minute or sometimes in seconds, while dE over dt is the rate of change of error. This controller, it's known as anticipatory control. That means it can predict the action of the process. So by doing the rate of change of the error, it can predict the output or the output of the controller. In case of there is no change in the error, the controller output here will be, what you mean by M, will be 0, since dE over dt equals to 0. As we have said previously, we need the derivative only to speed up the process variable or the dynamic of the process, since using some for example the integral part, and it will have the process getting slow. As we have said, that derivative controller cannot be used alone, so it could be used with the proportional mode or proportional integral. So here the output of the controller, due to the B, which is proportional and derivative modes, it will be MBD equal to KCE, which is this is the proportional mode part, plus KC TD dE over dt plus M0. Sometimes we add this one. This is the initial output of the controller. So this part is P, and this one part is the D, which is the derivative mode. Here is a graph that can explain the response of the proportional derivative controller to an error ramp, or the change in error. So if we have this error starting changing from this point, so we can notice that, for example, if this is 0, we can notice that at 0 the output of the controller change suddenly. This part is due to the derivative part. The rate of change now is different. So one of the main function of the derivative is to include or account for the change of the error in time. After that, we can see in this part that this part will be P plus D, which is the change due to the the output due to the proportional and derivative mode. So here we can see it. It's changing linearly with time due to the mainly the proportional controller mode. The derivative controller mode tends to speed up the dynamic process of the controller variable by decreasing the the process variable settling time. As we said, that it will speed up the process variable in order to get it as much as equal to the set point in short time. So what we call settling time is, as you remember, it's 5% from within the set point. What in case if the process is noisy? There is so many noise. It's fluctuating. The process is not clear or clean. There's some disturbances always in the process. So using the BD or the proportional derivative is not recommended, or using the derivative mode is not recommended in this case. Because once you implement the derivative mode, you will have a lot of fluctuating, a lot of disturbance also, because it will deal with every change in the error. The output of the controller will change, so you might get unstable system. Such as the flow measurement. The flow measurement, the change is so fast normally, and normally we have to avoid using the derivative mode in the flow measurement. While in the temperature measurement, the process variable changing change very slowly. So normally we have some derivative mode in the controller in order to speed up these kind of changes. One of the most important characteristics of the feedback control system is the stability. What we mean by stable system? A stable system is when the output response is bounded for all bounded input signals. Bounded means limits or restricted or defined upper and lower limits of the signal. So in case of the system or the output of the system exhibiting unbounded response to a bounded input, we call it an unstable system. So the bounded here means that the input variable that stays within upper and lower limits for all values of the limit. So this is in case of the bounded, but we needed the system to have bounded output to the bounded input. So in case of this unit step signal, as we see here, this is a bounded input. However, for the exponential function, we can see that this signal is unbounded. Here is an example of the stable responses. As we can see, here is underdamped system also, but finally they will reach the the set point. On the other side, we can see these are unstable system, since it's gonna be unbounded. So these are kind of unstable system. The instability of the system could be due to the many reasons. One could be incorrect action of a controller, or it's tightly tuned. That means we have to again do some tuning for the parameters. That means sometimes either large gain or sometimes a small or too small integral time, okay, or too large integral derivative time.